Good afternoon, everybody. So it's a pleasure for me to welcome you to this afternoon of celebrations. And indeed, on a personal note, it's really a pleasure to celebrate CECAM, with whom I had so many enjoyable and inspirational moments and discussions, many friends. Still remember the first workshops and the people I met there, the first workshop more than 20 years ago. So this afternoon of celebration will have two parts. The first part will have first a presentation on historical notes from Dan Frankel, and then we'll have the award of the Berni Alder Prize to Saro Suchi. And then after coffee break, we'll have a second part, which will be a roundtable discussion for the future of CECAM and the community. So without much further ado, I'll leave the stage to Alessandro Laio, who will introduce the first part and chair the first part of this afternoon.
Good afternoon, everybody. For me, it's a great pleasure and also an honor to chair this session. Let me say that when I entered the conference hall 2 days ago, and then I started seeing all these wonderful talks, I was somehow moved, because this gave me really the strong impression of how important CECAM has become in the recent years, and therefore how these 50 years were spent in a good manner. This birthday is for sure the beginning of something that will be even better, even greater than it has been so far. So for me, I'm really, really happy to be here today to chair this session. So the first talk of this session will be delivered by Dan Frankel. Well, Dan is the noble link between the community of molecular simulation and the community of statistical physics. So this thing is, well, somehow we all know that, but it is even certified by the fact that he received the Berni Alder Prize, which we are going to award also today, and also the Boltzmann Medal, which are the two most important recognitions of the two communities. Well, moreover, of course, Dan has always been a continuous source of inspiration for all of us. Well, I actually met the first time Dan in a warm pool in Iceland during a conference organized by Hannes Jonsson, who must be somewhere here in the audience. Well, already from the very beginning, so this warm pool, which we shared actually with many, many other people still also here in the audience, gave really the idea of what CECAM is, in the sense that we are a soup, a soup of people with a really fantastic flavor coming out of that. All right, so today Dan will not give a scientific talk, but he will actually talk about the history of CECAM, which has been rich of events. So I'm pretty much look forward to hear your talk.
In the meantime, I will use this microphone while you do whatever is needed to disintegrate. Take this away. Okay, so I'm indeed greatly honored to speak here. There's other people who have been involved with CECAM longer than I have, so it's not completely obvious that I should speak. I do remember the event in the warm pool. I actually have pictures that I will not show now. But I'm a bit hesitant to say too much about the advantage of being in warm pool, because I know that Giovanni Cicotti, when he thought that somebody was really not a very inspiring scientist, he would say, he's a boiled fish. And so maybe we're all boiled fish. Okay, so as I said, I'll give a very personal perspective of 50 years of CECAM, and I'll focus very much on the early history, which for a strange reason is largely lost in the mist of time, because CECAM moved several times, and every time this was an opportunity to lose the archive. And so I will focus on basically the early history and a few snippets of other things. But before I continue, I should really acknowledge the incredible help I got from many, many people. But in particular, Gianni Battimelli, who wrote a short history of the early days of CECAM that is incredibly useful. And then, of course, Sarah Bonella and Ignacio Pagadamara, who, in addition to organizing this wonderful meeting, have helped me a lot with getting some material. Now, before talking about CECAM, I want to place the whole thing in a context. And so I say a bit about the prehistory of scientific computing. Now, you all know the prehistory. Basically, it starts with a comment from the 19th century. Actually, I know this comment from Herman Behrens, who I think said the same thing at the 20th anniversary of CECAM, namely that every attempt to employ mathematical methods in the study of chemical questions, and this is not just chemical, must be considered profoundly irrational and contrary to the spirit of chemistry. If mathematical analysis should ever hold a prominent place in chemistry, an aberration which is happily almost impossible, it would occasion a rapid and widespread degeneration of that science. So that is what we are celebrating today. Now, a century later, some people, I'd say on the other side of the channel, had forgotten about Leconte's wise advice, and so they started to think about calculating machines. And actually, I'm proud to say that one of the first calculating machines in the context of quantum chemistry was built in Cambridge. It was called the differential analyzer, and it was built by my predecessor, John Lennard-Jones, who built the machine out of Meccano. That's a now lost British product that was incredibly useful to tell children how to work with stuff. And they built this machine that actually was used to do integrals. But of course, that's 1938. And then during the war, in the Second World War, in several places, electronic computers were being developed, and so the picture that we normally think about when we think of the early history of computing is the early history of electronic computing, and this is John von Neumann. You see him, he was the maniac, and there actually was at some point an article called John von Neumann, the Maniac. Okay, so here's John von Neumann, and at some point, around 1953, a bit earlier, people at Los Alamos were interested in exploring if electronic computers could have any other applications than just developing nuclear weapons. And that was the task that Metropolis got. So Nick Metropolis was asked to explore what was possible, and he got in contact with a number of people, for instance, Fermi Pasta-Ulam, but also the Rosenbluts and the Tellers, and this resulted in the first Monte Carlo simulation paper. And I have a short movie that I'll show, and hopefully it will work. Wait a second, this I can't do with the remote mouse. But now I lost the other mouse, so I never quite know what that is. I see it lighting up, because if I have to do it with my... this is so irritating. Sorry? Sorry, I tell me. It's above. Is it? Not anymore. No, sir. What?
You're looking for the.
Yes, I am.
Okay.
Very strange. But anyway, so this is Marshall Rosenblut explaining at the 50th anniversary of the Monte Carlo method that actually, if you listen carefully, they were interested in doing these calculations. Come on. Now I thought I had it, and then I...
Fine, yep. So that we then set out to work, and of course our first thought was the obvious one of molecular dynamics.
Okay. Our first thought was the obvious thought of molecular dynamics, and then he explained it was too expensive, etc., etc. So the idea of molecular dynamics, and he actually says something, he said it was obvious, and indeed it is obvious, but Monte Carlo, Metropolis Monte Carlo is not obvious. But anyway, so this developed in the US in Los Alamos, later Livermore, and then also Argonne. So it was typically the national labs where computer simulation came into being. And so then the question is, you can ask, why was CECAM created? Because that's a very non-obvious thing. And I'll develop a line of thought that not everybody may agree with by going back to what Thomas Watson, the first president of IBM, once said about computers. Because he said, I think that there is a world market for about 5 computers. And actually, if you look at the situation in the early 50s, then powerful computers, by that standard, powerful computers, there probably were about 5. And so this meant something for what you needed if you wanted to develop computational science. It would basically mean that you needed access to a very rare and expensive machine. It is like at the same time they were building CERN with the accelerators, and clearly you needed to be near the machine because internet didn't exist, so the data were generated locally. You had to be there. And that is something that was very important because actually throughout most of the 50s and the 60s, the powerful computers were in the US. Not all of them. There were some computers for other applications in Europe. And of course, mostly they were not dedicated to scientific computing. And so Europe was really lagging far behind the US. And so there were developing in the different European countries, local computer centers, again, not primarily scientific, although universities had local computer centers, but they were not very powerful. And so here I'll show you a picture of me as an undergraduate student. I mean, initially you will not see which one I am, but the main thing is that we actually used computers for data analysis, and the point was that the machine that we used, which was then a relatively advanced CDC machine, had 32 kilobytes of memory and a floating speed of a few hundred per second. So that more or less limited what you could do, and this is me. Okay, right. Now, what happens here then in France is that the CNRS obtained a, by that time standard, very powerful IBM machine and placed it in Orsay. And the thing that was unique about the IBM and Orsay, it was fast, sorry, I have to go back. It was fast, and it was dedicated mostly to scientific computing. And this is where Carl Moser entered into the game. And so here you see Carl, the way you normally see him depicted with his dogs. But we've talked already quite a bit about Carl Moser, so let me show you one movie of Carl that actually was taken at the 20th anniversary of CECAM, where he was explaining that he was taking care of the CECAM budget, and so that exceptionally, in this case, the coffee would be free.
Chance for coffee this morning, and untold generosity from the CECAM, the coffee is free of charge.
Okay, good. Coffee is free of charge. Carl kept a close eye on the budget, which is something that Giovanni later as director took advantage of and then spent most of it. But Carl saw this thing, that you have this unique facility, you want to do scientific computing, so we have to do something that is not just local, we do something international, and he was a quantum chemist. If you want to know more about him, you have to read Battimelli's article. And he had a strong European and US network of quantum chemistry professors, and he felt that there should be an international center around this unique facility. It is a bit like they built an institute around CERN. And it was, in that sense, very similar to what Nick Petropoulos had done with the Maniac. So you just want to see what computers can do. So it was not computer science, it was really computational science. Now, the computer was housed in a building in the campus of Paris Sud in Orsay, and so was CECAM on the 3rd floor. Sarah and Giovanni and I, we've all been looking for a picture of the building, but it's so ugly that nobody in the past 50 years has taken the trouble of taking a picture of it. And so, fortunately, with Google Earth, I could find a picture. So there you see it. And this, if I ever can get this to work again, this is basically the CECAM floor. Anyway, so that is where it was all located. And CECAM had a focus. I mean, there were certain things it was not doing like computational fluid dynamics at the level where particles don't matter. So it was everything where particles matter, atoms, molecules, electrons. It may be in astrophysical plasma, but the particle nature was important, but not high energy physics, so not extremely small and also not extremely large. Now, I think that choice for the topic was also due to the fact that Carl Moser was a chemist. So he cared about atoms, molecules, and materials, as I think this community largely still does. Now, the CECAM, as we know it, started in 1969, although according to the CNRS books, only in 1970, but that's a technical thing. And it started first with long-term scientific visitors, and the workshops came about 2 years later. Now, I will just show you an example of a workshop. Again, it's a movie, because the workshops, as they are now, are things where you have meetings and discussions during the day, although there was much less talk and much more work, because it was a local computer that you could use, and that was more powerful than a computer at home. And here you see after-hours discussion. Oh. I hoped it would be, but I seem to be totally unable to get this thing. I temporarily switched off the sound, but basically, you see there are napkins, and so you can do science. Now, you can do science, but you can't. I mean, we can't move this thing. It's always okay. So, Carl Moser, at some point, moved beyond just quantum chemistry, so he traveled a lot. As a CECAM director, I think that the CNRS was always concerned how much money he spent on travel, but it was actually money well spent, because he wanted to know what was going on. And so just to show how much he interacted, so I don't have any evidence from the 1960s, but I have a fairly early email, because I don't throw my email away, 1987. And here you see that Carl wrote, "I'll be in Livermore and on my way to New York." So this is typically Carl. I was traveling all the time. Now, the main thing is that in the late 60s, he was talking to Wim Newport, his quantum chemistry colleague, met Herman Berendsen, who was very excited about Raman Stillinger simulation of water, and they decided at a meeting in Barfum that I have not been able to trace, to start something in the area of molecular dynamics simulations. And this environment at Paris Sud at Orsay was ideal because there was a top group. I mean, basically the leading group in Europe in the area of simulation of liquids. There was Lou Verlet, Jean-Pierre Hansen, Dominique Levesque, Jean-Jacques Weiss, and Vieira Baron. And they had basically been pioneering MD simulations as a tool to test emerging liquid state theories. Now, the point is that there was not an automatic good interaction between the two, but then there was a visitor, Gianni Iaccucci, who was Italian, a long-term visitor, and he made the contact with the Paris group. He went there every week, at least once or twice, and he also made international contacts with Anis Rahman, Ian MacDonald, Conrad Singer, Mike Klein, etc. And he had a local team that involved Giovanni Cicotti, Jean-Paul Ricard, who are here, and many, many others. I thought I wouldn't. And so the one thing that he also succeeded is in obtaining Verlet's MD code. Now, how do you know if you have obtained Verlet's MD code? It is because in that code, the unit of time differs by a square root of 48 from all subsequent or earlier codes. So if you ever see somebody with the unit of time is a square root of 48 different, you say, that's the original, that's a descendant of the original Verlet code. So it's in the genes. Okay. We couldn't get any comment from Gianni Iaccucci until this morning, and so Gianni just wrote to me this. He said that this being at CECAM gave him a feeling of power. Anything was possible. The main features were substantial computer power, as I said, freedom and respect for individual research objectives, and huge opportunities to choose and follow one's own project success. Not rarely an outstanding scientific success. Life and science at its best. Okay. In the 1980s, 70s and 80s, CECAM community expanded. And so how do you quantify it? Actually, there was a meeting at Argonne in 1984 to celebrate Anis Rahman. And quickly, during the past few days, I circled a few heads on the photograph that have strong links with CECAM, and are in the sense that not just that they influenced CECAM, but they were frequently there. And so here you, I really don't know on the... Oh, you see it. I didn't see it. Okay, good. Yes. So this is just the number of people. Actually, Carl Moser is somewhere here, I think. Never mind. This is something you can look at in more detail later. Now, the thing is, and that's the question I want to address. This was a wonderful situation. Everybody loved Paris. I mean, you would take the RER into the city center, you have dinner, etc., and discuss things. So why did CECAM leave Orsay? And what I now say is my personal opinion. I haven't checked this with anybody because then probably I wouldn't be allowed to speak. And so I think that the reason why CECAM had to leave Orsay has nothing to do with conflicts between personalities, etc., etc. It was basically that the original CECAM model that Carl used to build it was no longer relevant. And to explain that, I said, CECAM initially was like CERN, a very expensive facility of which there's only a few in the world, and you had to be nearby to exploit it. Now, that is basically the situation that's still true for accelerators. They're still very expensive and unique. And if you look at the really big accelerators, it is like Watson's 5 computers. There may be 5 really big accelerators worldwide. But then something else happened, and that's something you could call market pull, something that the high-energy physicists have never suffered from. And basically, the power and the number of computers exploded, and they were accessible from any location on Earth. Now, I don't want to be facetious, but I basically, if high-energy physics, if the equipment had developed the way computing equipment had developed, then we would all have a hadron collider in our mobile phones, and they would have been much more powerful than the LHC. That is just to give you a feeling for what has happened to computing. Now, the other thing that, of course, was very important is that computing power has increased, and we know the Moore's law, etc., etc. But in many cases, and that's where CECAM again was extremely important, the main developments came from algorithms. The gain in computer power is often, and actually when Saru Suchi speaks later today, we'll see an example. The gain in computing power is often completely overshadowed by the increase in the power of algorithms. And I just mentioned as one example, the rare event algorithms developed by Bennett and Chandler and later by Delago and Bolhuis and others and Geisler. So these are things that made orders and orders and orders of magnitude difference. So basically what happened during the 1980s is that the emphasis shifted from using the Orsay computer to meeting at Orsay and to discuss algorithms and new applications area and do most of the applications at home. And basically that could literally be at home. By now you do it on your laptop if you want to. And so the access to the Orsay computer as such became less and less of a factor. But I think that at that point, the CNRS hadn't realized that. And so that was the core of the problem, because in 1992, CNRS wanted to make a major investment to upgrade the Orsay computer, the supercomputer, which a very laudable initiative. And so they wanted to build a computational center around it. And the idea was then that CECAM would be still allowed to remain and would be part of the center. And the CNRS president at the time said, it seems desirable to us that CECAM becomes the European component of this laboratory placed under CNRS responsibility. So if I say it in a very distorted way, basically the CNRS said, well, to all the international partners, yes, you can keep on paying and we'll actually be in control, which was a very nice offer. And so to be more explicit, and that's why you see the role of the supercomputer, the then CNRS representative on the CECAM Council wrote, the CNRS management of CECAM is required by the very strong coupling that we intend to set up with the future computing center. But that was outdated. And so the CECAM president, who was actually also in the room at the time, he then asked, so there was a council meeting, and so I actually asked the members to consider explicitly how much the independence of CECAM, for how much your organization is willing to trade in exchange for the possibility to have access to the supercomputers at Orsay. And the answer at that time, of course, was very little. I mean, I tried to think of an example what in another walk of life. So I thought it is a bit like if you say, oh, we have writers. Writers use papers. So let's make sure that if we set up a writers collective, we do it next to a paper factory. That was more or less the situation for CECAM in the early 90s. There was no real need to be close to a computer center. And so CECAM had to move to Lyon. And so here I have a trajectory. You see here Orsay, and there you see Lyon, and then CECAM basically in a very stormy movement moved like this to Lyon, although some people predicted another trajectory, but okay, that's something else. Good. Right. So, how did this all work out? Now, again, I don't want to make a false comparison between CECAM and CERN, although I can't quite completely ignore it, because in 2018, I just looked at 2018, the budget of CECAM was around 2 million euros. For CERN, it was a billion euros. And I write here, I will not make the cheap comparison of the cost per publication, but if I tell you that CERN published 1,402 papers in past year, the equivalent number of papers for CECAM would have been 2 to 3. Now, you can decide whether our community has published more than that. And of course, then there's societal impact, because if you look at all the things that are happening in material science, in biology, etc., that is, I think, extremely important. But the curious thing, and this is actually where I would like to end, is that although we think that in terms of impact on society, the computer simulation, computer modeling is incredibly important, the visibility of simulation is much lower than that of CERN. And so we have to address one question, that is, what are we doing wrong? And so I take an example of one person who is, again, very important in the CECAM history, be it not a CECAM-involved person. This is Nick Metropolis. There you see him. So this is early computer chess at the time that probably even I could still win from a computer. And so, I mean, in our field, the name of Metropolis is extremely famous. The Metropolis paper with Rosenbluth, Teller, and Teller has been cited close to 40,000 times. So that we would call in science a success. And then you go to Wikipedia and you think, so who was this guy, Metropolis? And it's actually very interesting, because here you have him. You see the picture, a young Metropolis. Later on, he was older, and that's important because you'll see him again. Because one thing is that it says movies. Nick Metropolis movies, yes, husband and wife. And indeed, I checked on the internet. That's what internet is for. And you can actually find here husband and wives, and you look at the cast, and there, indeed, is Nick Metropolis, TV scientist. Okay, now we're getting closer. So we have a TV scientist, and so here you can actually rent DVDs with Nick Metropolis movies. And so here I have the movie, and again, you'll find he actually says something, and hopefully you can hear it, otherwise I'll be happy to repeat it. But here he's speaking about Einstein's 70th birthday party, and that Einstein said that the good Lord doesn't gamble. And then somebody else says something else that I'm also willing to repeat at the end. Oh, no, I know what happened. I switched off the sound because it was too irritating. So I have to go back to the beginning, and now I switch off the sound full power.
Einstein was then celebrating the 70th birthday anniversary, and there was a colloquium given for him. And he said, God doesn't play dice with the universe.
No, he just plays hide and seek.
He just plays hide and seek. But I mean, that established the career of Nick Metropolis as a celebrity. And so that's what we're up against. It's going to be extremely hard to do it. At the same time, I think that if with CECAM we continue in the way that we do now, we are really on the right track. I'm incredibly impressed by how this meeting has been organized, except that this meeting has been organized with the same professionalism and the same so frictionless, I mean, almost invisible organization behind the background as all other CECAM meetings I've been to in recent years. So I think that we can be very optimistic about CECAM. And so I have a very classical birthday card for CECAM, more or less from the early days. And if you can read here, it says, "Happy birthday, CECAM." And I'll end with some images from the reception at the 20th birthday celebration CECAM. And I'll put the sound a bit louder, softer, because they're very loud people. I mean, I don't know who that is, but it seems to me. Okay, so, and with that, I should like to thank you all. And I don't know whether there's urgent questions, I assume not, but otherwise we just move on to the next part of the program. Thank you very much. I'll stop it.
Okay, thanks very much, Dan. I think we should all make the strong effort to apply to TV shows, places, singing contests. We have to make ourselves more visible, and always talk about dices. This is also extremely important. So now, No, it's only just the session continues actually with a very important event in this conference, which is the awarding of the Berni Alder Prize. The Berni Alder Prize was established in 1999 while Michel Maréchal was a CECAM director at Lyon at that time. So the prize is awarded in recognition of exceptional contributions in the field of molecular simulations. On the CECAM webpage, we claim it is the most prestigious prize in this field, but actually the prestige of the prize is actually mostly demonstrated by the name of the winners. So the name of the winners, the previous names of the winners are really the founding father of our manner of making science. So the first winner of the prize is Giovanni Ciccotti. Then it was the time of Kurt Binder. Then Mike Klein, then Dan Frankel, followed by Roberto Carr and Michele Parinello, followed by Berensen and Jean-Pierre Ansen, and finally 3 years ago, David Sepperly and Hardy Gross. Many of these winners are actually here in the audience today. Well, I guess that these names to our community really need no introduction because they provided such an important contribution that basically our community would not really exist without them. So the name of the winner of this year is Sauro Succi from Italian Institute of Technology, and I think we should really cheer him with a warm round of applause. Well, Sauro Succi, so the beginning of his scientific career is actually is pretty weird because he's a nuclear engineer. When I read this thing in his curriculum, this made me feel a little bit less like a black chicken because I'm also a nuclear engineer. Therefore, well, the idea that I'm not the only nuclear engineer in the community made me feel great. After this diploma, he actually immediately changed his mind and he moved to physics. Yeah, and he came actually here at EPFL and he took a PhD in plasma physics here at EPFL. Then, well, he was throughout most of his career so one of the authorities in theory of CNR, National Council of Research in Italy, and only very recently, I think 1 year ago, he moved to Italian Institute of Technology, where now is actually working on something which is related to medicine. So also a remarkable change of subject and of field. So like all the other prize winners, well, Sauro would not almost need an introduction because the result of his work is basically known to all of us. It is lattice-Boltzmann, the manner of treating and exploiting efficiently lattice-Boltzmann to obtain reliable information on on something which is fluidodynamics. No, so this thing. The simple, let's say, simple idea of using a lattice model to obtain information on something which, by definition, moves around like fluids is really extremely brilliant. Is in a way a strong demonstration that not necessarily, in order to obtain a more accurate model, you need to do something that looks like reality, no? So one qualitative one might think the more realistic I am, the better I am. Well, lattice-Boltzmann is actually a demonstration that this is not the case. In that case, the particles are really used as mathematical tricks to represent in a manner which is computationally efficient the mesoscopic scale behavior of fluid. So this approach has proved extremely fertile, and nowadays is also the basis of multi-scale approaches. Therefore, I'm really extremely happy that this prize was awarded to him. Last thing that I want to say, that like in the cases of all the important contribution, an enormous added value is when this contribution builds a bridge between different communities. And so in this case, lattice-Boltzmann and the work of Sauro Succi is a bridge between the community of molecular simulations and the community of fluidodynamics, with all that this means, because fluidodynamics has enormous technological and practical importance. So the capability of letting our community to talk to this other community is really extremely important. Well, Berni Alder, to whom this prize is named, in the last edition of the prize was actually attending the ceremony. This year he didn't manage to come, but he was so kind to send us a short video where he basically greets the winner of this year, and he also describes in his perspective, which is an historical perspective, the birth of lattice-Boltzmann, mostly during the 70s. So this video is really very interesting because it contains a lot of historical details on how this very important method was born at the very beginning. So I think now, if possible, I would ask to our staff to put on Berni Alder's video. Right.
As for the Sauro Succi Prize, I want to first of all, he made his work mostly in lattice-Boltzmann, And I may want to first tell you a story which many of you probably don't know about the origin of lattice Boltzmann. Lattice Boltzmann started with an announcement from Los Alamos by three very prominent physicists, Fritsch, Pommeau, and Hauslichter, and they announced that they had found a method to solve all hydrodynamic problems in a microsecond, or some words to that effect. And they published it in the New York Times. And that caused quite a stir at the weapons laboratory like Livermore, because hydrodynamics is one of the foundations of weapons design. So the director of the Lawrence Livermore Lab came to my office when he saw the New York Times item and said, "What is this all about?" So I decided to look into it, and my first reaction was that it is poor molecular dynamics. And indeed it is, but that's not a negative remark, because we are all poor in molecular dynamics, because we really don't have the computational power to do hydrodynamics and other problems well. So after investigating, we are poor because we don't have the computer power to really do big problems. So the key thing to me about lattice Boltzmann is that it is the fastest method, particle method, to do hydrodynamics. And the first thing we did, I did that with a postdoc after this visit from the director of the lab, and found that if you take enough lattice points, then you can in fact do the equivalent of Navier-Stokes hydrodynamics. So after we discovered that, many people took up lattice Boltzmann, and Soury did many applications. But I want to tell you about one that illustrates that it is the best particle method to do turbulence, the onset of turbulence. And I got Sora involved to help me with that problem. And let me tell you briefly what that problem is. When you use lattice Boltzmann to do hydrodynamics, you have several advantages. One, you can deal with the more complicated boundaries. For example, we needed a little bump in the pipe to get turbulence going in the flow at high enough Reynolds numbers. Then we could show that it's very easy to introduce fluctuations into lattice Boltzmann, which also introduce the onset of turbulence. And finally, we have an H theorem for the lattice Boltzmann method, a modified H theorem, which we have implemented, and that guarantees numerical stability to the flow. So all these advantages, and the fact that it is, the key thing is it's the fastest method, particle method, to do hydrodynamics, which guarantees stability, numerical stability, because very often when you do any instability, like for example, if you introduce fluctuations in Navier-Stokes, you run into terrible numerical instabilities, which we originally discovered and had to use very complicated methods to overcome. Anyway, when we did finally do lattice Boltzmann as the only possible way to get into high enough Reynolds numbers to get into turbulence, we discovered that there's a mechanism for the onset of turbulence. And for example, before the onset of turbulence, there is a steady state predecessor to turbulence, which involves a vortex formation in the boundary layer. What happens is at low Reynolds number, you have a parabolic profile. And as you get closer and higher to higher and higher velocities, higher and higher Reynolds numbers, that parabolic profile changes to an almost square well profile. The parabola flattens out and the sides become very steep. And then in these very narrow boundary layer, the first vortex forms before turbulence sets in. The problem is, and the reason I needed Sauro's help, is that the Reynolds number at which we find with Lattice-Boltzmann, at which turbulence sets in, is a factor of 2 lower than the experiment is a factor of 2 lower than what the computer shows. So the reason I believe that that is true is that you on the boundary layer, you can no longer use what I call linear hydrodynamics. That is, you leave out you can't leave out the higher order viscosity terms and so on. So what one has to do is at the boundary layer, one has to put in full Boltzmann equation, a full non-linear Boltzmann equation, called by a computer method called DSM-3, which it was invented by boys many years ago. And what Sara did is he matched, where you have to match the algorithm of full Boltzmann equation with the lattice Boltzmann equation. And Sara wrote a beautiful paper just doing that. So we hope to use this method to show that these non-linear terms do matter and change the onset of Reynolds number of turbulence by a factor of 2. But Sara has used the lattice Boltzmann equation in many different ways, taking advantage of some of its features which one cannot handle well by Navier-Stokes. So good luck, Sara, and congratulations to winning the prize. Thank you very much.
Okay, after this video, which was very, very interesting, I think it's time to leave the stage to Sauro, who will give us a presentation of his work. I think that you can directly use this.
No, it doesn't seem to be operating. Okay. The audio? Yeah, keep it. Okay, so good afternoon, everyone. It's a great day for me, and I hope I will deliver. If not, I can blame it on the jet lag, but the reality is that I feel really emotional today for many reasons. The first being that besides admiration for Berni, I have a true affection to him, and I will explain you why. But before I even start, I want to thank CECAM, wish happy birthday. I mean, I got familiar with CECAM through Michel, who is sitting in the second row, some, 30 years ago, so I have a long enough record. And today, I will try to, first, since I feel emotional, and probably you see that, I want to start right away to tell you why I'm emotional, and then I will try to give my own reconstruction of the way lattice Boltzmann developed, since I had the good fortune to be around basically from day one. And of course, Berni, now he made the message quite clear. I'm very happy to share the Berni Alder Prize with Berni himself, because he really did significant contribution at the beginning, although I don't agree with him that turbulence is the best application, but that's a separate story. Okay, so let me tell you why I am emotional. And you see, because I can't even move the... Okay, back. So these were the days, Berni, Tony, and me. It looks like a comedy. It is not. And we are talking 1992. And in that picture, how do I zoom? Yes, like this. There was a beautiful conference organized by Michel in Alghero, which really marked my scientific life for sure. And I tell you why. Berni was giving his speech for the 65th anniversary. He was just turning 65th. He didn't change much, which does not apply to me, neither to Tony. Incidentally, this proved that I was not born white-haired, by the way. And this meeting, Berni was just discussing, saying, look, at the end he said, I don't care. Can you hear me at the bottom of the room? Okay. Said, I don't care about money, never did. I don't really care about aging. Not sure he was lying, maybe. The only thing I care about is I regret that I'm getting old, because I know I will not have enough time to see the solution of the problems I've devoted my entire life to. And at that moment, Berni was almost bursting in tears. And you know, to me, I was a young man, and to me, Berni, I barely knew him, but it was obvious that he was a thick-skinned guy. I was so astonished and very moved. And I distinctly remember, as we speak, that I thought, what a wonderful thing. That's the way I want to be at that age, and I'm getting there. And I thought to myself, that's really what I want to do in my life. So in that respect, I'm really very grateful to Michel for organizing this meeting. You know, I was just beginning, and there were Feigenbaum, there were Prigozhin, and I was saying to myself, what am I doing around this list of names? So it was really a marvelous and very, very important event to me. So now Berni was regretting about time, but actually just, oops, the other way. This is just the most recent time we met, and almost 30 years down the line, Berni is still very active. As you just learned, he wants to crack turbulence, and under, I would say, a reckless invitation by Giovanni, the 91 years young man traveled from New Jersey, visiting his daughter, to Rome on Wednesday, back on Sunday, alone. Okay, that tells you about Berni, 91. And I got an email, say, Sauro, I'm in Rome 3 days, we have to talk because we have to solve the turbulence problem. And you heard about that, and I would say it's working slow process because things don't move very fast. But nevertheless, this tells you why I love him, and I really feel very much indebted, and I think he really represents something very important in my scientific career. So now I keep going the other way. Now the story, I had an option, of course. Either I could make a scientific talk and say where lattice Boltzmann stands and where it's going to be for the future, or play the old man story, and I chose, in fact, definitely the second option, because I think it would be interesting for this audience, especially for the youngest one, to know how the story developed. Berni has his version, I have mine. They not necessarily the same, but by and large, say, in a weak norm, they converge. So we're talking the Jurassic here, okay? How the things developed in the old days. And I must say, as always the case, there are many, many smiles of Lady Luck in this trajectory. I will just mention the most important one. The first one was that at that time I was just moved from this place, from EPFL, finished my PhD in plasma, and I went to a center which is called IBM Center for European Scientific Computing. Incidentally, Alessandro spent almost 10 years there before I went to CNR. And my boss, my task was I was working in the group of fluid dynamics with Roberto Benz, who was my boss, and my boss Square, and one day stepped into the office and said, Sauro, why don't you just give a look at this paper, Cellular Automata, Supercomputers for Fluid Dynamics by Tommaso Toffoli and collaborators. And you know, these were the days where there was big fuss about the entire world being a cellular automaton, right? And Stephen Wolfram is still pretty much in this mood. So what they showed in this, why the laser is not working? Anyway, what they showed in this, as you can see in the bottom row, they showed that by running a cellular automaton, this is a Boolean game in the square lattice. I'm sorry, I cannot operate the square lattice. They were making claims that this cellular automaton was supporting, in fact, sound waves, as you can see. Noisy, but sound waves. So my job was to reproduce the things and try to see whether we can do turbulence with this automaton. And I must say that incidentally, I had to learn, my only mandate was to learn how to program IBM machines. And then I would say, and I did it even in assembler language, which proved fun beyond expectation. I wouldn't do it twice, but still. And what I got, actually, I got the sound waves, but when I looked into real fluid dynamics, which is vortices, what I got was weird. I got square vortices, which really do not seem to belong to this planet. Okay, so why were the vortex square? Well, in hindsight, this was pretty obvious, because if you look, I'm not sure you can see that, but in the 2 weeks before that, the same journal, namely PRL, published The Real Thing. And The Real Thing is what Berni was just mentioned. This is the famous lattice gas Frischers-Lacker-Pommeau. And incidentally, I have to say that if you talk to Stephen Wolfram, and I'm talking Wolfram, the Mathematica Wolfram, there is a very interesting story for the history of science, because he feels that he has a lot of priority here. But for the record, it's Frischers-Lacker-Pommeau. And what they did is what just Berni was saying. They showed that if you just move from a square automaton to a triangular one, then you get real fluid dynamics, okay? So the vortices are no longer square, they are circular. And there was indeed, I don't think it was the New York Times, not to my knowledge, there was a big story on the actually Washington Post. If you read through, at some point they say, this is so important, because that's the way fluids will be done in the future, and it should be kept out of the Soviet hands, which means, actually, there should be a movie coming in. There is even a James Bond flavor in the lattice Boltzmann story, and for the record, James Bond is just 6 years older than CECAM, okay? So it was a very interesting big waves into the fluid community, but at a closer inspection, there were several problems, okay? And I will just mention the three most practical ones. The first one is noise, okay? Noise. The second one is the fact that collision operator is exponentially complex. If you have an hexagon, the complexity is 2 to the power 6. But when you have to design an airplane, you are not in 2 dimensions. You have to go to 3. Actually, you have to go to 4 in those days. There is no lattice in 3D fulfilling the symmetries. And B, in that case, is 24, which means 16 mega operations per lattice site, each and every time step. You can imagine the reaction of serious computational fluid dynamics. They were laughing at it. And to add insult to injury, even navigating through such a large phase space is kind of miserable, because there are very few of these configurations which are compatible with the conservation laws that collision operator has to obey. So the end result is that the mean free path of the lattice gas is very high, and I mean free path means high diffusivity, means low Reynolds number, means no turbulence, okay? So this was very interesting from the conceptual point of view, but from the point of view of fluid dynamics, it was not really up to the expectation. Now, let's start from the noise, because that was the way lattice Boltzmann was originated, and I did my exercise. This was my first PRL, and to make a long story short, this is Roberto Benzi, my boss. Back in '88, he was doing fancy 2D simulation. This is, again, you can see the quality of this board. This was state-of-the-art pseudo-spectral method. My job was try to match this, And so we set up a world record by the time. We set up an 8,000 square lattice gas automaton. And if I show the picture of the 8,000 square, what you see is the broken TV. There is no signal whatsoever, it's just noise. So what do? You coarse grain, you take boxes, and you extract one floating point every 64 square lattice gas automata. And indeed, the coherent structure, they emerge, they swim into the noise, they are more or less circular, and qualitatively, they are basically on place, and PRL got accepted. Big success, except for one little detail, that when you measure the performances, pseudospectrum was winning by a factor 1,000 at least. So you can imagine, you can guess the reaction of the boss, which is written there. Excellent work, guys. We even got a prize for that internal IBM, money prize. But you please move to something else, right? So, and that something else was, in fact, lattice Boltzmann. But before I go into that, let me actually mention the earliest, for the record, lattice Boltzmann, the earliest paper where, in fact, the word Boltzmann comes associated with the lattice gas is by McNamara and Zanetti. And here I have to convey, I'm very sorry, to convey a very sad news that Gianluigi just passed away a few days ago in an air accident, small plane. So I salute Gianluigi, and I give him the tribute he merits, because the conceptual idea of getting rid of the noise, and they were working with Leo Kadanoff in Chicago, belongs, in fact, to this paper. What they did basically was to realize that since, in the end, what you want to do is Navier-Stokes, why should you just... The lattice gas is a many-body system. It's a Boolean many-body system. Berni used to call it maximally discretized molecular dynamics. It's an amletic fluid, to be or not to be. Either you have a particle or you don't, 0, 1. And then you make the automaton actually graded. They replaced the Boolean occupation number with the probabilities. The probabilities are distributed between 0 and 1. And it's basically a noiseless lattice gas cellular automata. I think the best definition comes from Dan, which calls it a pre-average lattice gas. That's what it is. So that was a major conceptual step, but all the other problems stayed. And here comes, I would say, my biggest smile of Lady Luck. Javier Jimenez, who is a professional turbulent guy, invited me to Madrid because he was also working at IBM at the time. And as a result of this visit, we agreed that his student, Francisco Higuera, would visit me in Rome, IBM exec. And Francisco came. I was still struggling with my noise problem. And he came with pictures which were looking smooth. I don't show them because they're pitiful, but nevertheless, they were smooth. And he said, Sauro, forget about the lattice gas, let's try to do something else. And they were also up to the lattice Boltzmann, except for one little and crucial detail, that instead of performing the full collision operator, okay, since again, it's always the same story. Ultimately, you want to solve Navier-Stokes. That was the mandate, nothing else but Navier-Stokes. You know that there is a local equilibrium underneath hydrodynamics, otherwise Boltzmann would not converge to any hydrodynamics, and you know what the actual equilibrium is. And they find a very nice and very astute recipe to boil down the exponentially complex collision operator into a matrix vector operation, so to say. In computational terms, that means turning a problem which is 2 to the power 24 to a problem whose complexity is 24 power 2. And there is a difference, right? So that actually removed the second big barrier, which was exponential complexity. It didn't remove, though, the fact that the mean free path is still miserable because this matrix Aij, which you could pre-compute beforehand, okay? It's a constant. That's really non-trivial. Still, this would just do the very same number of collisions that the lattice gas, underlying lattice gas, is doing. So again, no real high Reynolds number, but we could actually run what is, by fact, the first lattice Boltzmann simulation of a nonlinear flow, and the results were pretty much on target. So I would say this paper is not well known, I would say, but is in fact the first simulation where you show that this computationally viable form of the collision operator does reproduce quantitative hydrodynamics, but low Reynolds. So again, Berni would not be happy. There is no real turbulence here. Next step. And here I shouldn't say because I'm in the author list, but I regard this as, frankly speaking, one of the game-changing paper in the and it all happened within 3 months, by the way. If you look at the dates, we are talking the first semester of 1999. Having realized that we can actually work in terms of a scattering matrix and the local equilibrium, which we know, and I have to, again, give credit to Roberto for contributing to this work, conceptually contributing, why not moving the other way around? Say, why not specifying, actually, the collision matrix in such a way that you start from the target, top Navier-Stokes, so emergent to me means molecular dynamics, and you go up to Navier-Stokes. You start from the target and you design the scattering matrix in such a way that you reproduce Navier-Stokes. And by then we knew the ropes because we knew the symmetries which were needed. And the idea is really sweet. The idea is that you just pick up, if only I could memorize. You know, this is a spectral representation of scattering matrix. The eigenvectors we knew because they come from the lattice symmetry, so no brainer. And the idea is just pick up the eigenvalue as you best like them. Some eigenvalues have to be 0 for conservation. The first non-zero eigenvalue will tell you the viscosity. And that was true. 2 consequences. Practical one, that we could choose the mean free path. And actually, we could bring the mean free path way below the lattice spacing. And that made lattice-Boltzmann competitive towards real computation for dynamics. At that point, we could do I Reynolds, as high as permitted by the resolution, like anybody else. But in hindsight, I would say definitely more important, we cut the link with underlying lattice gas. At that very moment, lattice-Boltzmann became a standalone, okay? Because there are good and bad sides at the time, and in those days, we only realized the good ones, and that's why Lady Luck was really smiling very high to us. But I think this was really the most important and influential contribution, that you start thinking of lattice-Boltzmann independently of any underlying physics. Of course, if you are a fundamentalist in statistical mechanics, you are not very happy at this move. And I promise it took to me at most 10 years, almost 10 years, before I stopped having the question, are you really solving Navier-Stokes? Eddie Cohen, who unfortunately passed away a few years ago, I remember was constantly asking this question, and in perfect good faith. People would not believe that this would give Navier-Stokes, but it actually does. So, and then we started to have a lot of fun. We did turbulence, and we could reproduce actually the beautiful vortices. Now I could basically fill my mandate. We were competing with pseudospectra, pretty much on target. But we felt, and again, Berni would be disappointed, that there were other applications where lattice-Boltzmann would be even more actually useful. And we did basically everything, magnetohydrodynamics, just for fun, frankly speaking. The driver was fun, period. But I think if I have to pick up one which stood the test of time, I think lattice-Boltzmann is still, I would say, a mainstream method now for porous media. This is the first lattice-Boltzmann simulation of porous media. It's a miserable porous media. This was done on a 128 cube, which was a rather heroic calculation in these days. We are still talking 1989. Many of you were not born. And I would say it stands to this day. We did many others didn't become mainstream, including, I would say, turbulence. I would not consider turbulence as a mainstream of lattice-Boltzmann, not at this moment at least. So, and then we had a couple of few very happy years where actually the method was picking up, people were starting to use it until, unfortunately or fortunately, we were blocked off by the French. And I don't have a picture of Johan Qian, but this paper is enormously cited, and deservedly so, because they realized what we should have realized. In hindsight, everything is clear, but they say, look, since we are only looking at Reynolds number as a parameter of your problem, why would you use a matrix? Why not just using a single relaxation time, which, by the way, was known in statistical physics since 1954, as old as I am. called BGK approximation. And they boiled down, actually, they found a way of constructing the local equilibria in a very systematic way. Don't go through the equation, doesn't matter. I only want to say that till then, we were constructing our local equilibrium by patchwork. It was painful. In the end, you get the result, and you can run your code as long as you want, but you have to derive them painfully. And they wrote down the lattice-Boltzmann in single relaxation form, and that is still the form that you would use today. When I give it to my students, most of the lattice-Boltzmann work is still done on this form. And again, if you go to a mechanical engineering, fluid dynamics engineering conference, and you say that this is solving Navier-Stokes, and they will laugh at you, you are kind of sympathetic, right? It's hard to believe, but it really does. So, 1992, and there is, well, that would be too technical, but let me tell you one thing. We constructed the lattice-Boltzmann based on the conservation constraints. And we, frankly, at least me, we totally forgot about Lady entropy. We didn't think of the second principle. And this is technical. I will try to be quick because it's really... Lattice-Boltzmann, as you can see from this expression, there is a weird expression for the viscosity as a function of the relaxation rate omega. And you can immediately spot that omega has to be between 0 and 2, otherwise the viscosity goes negative. If omega goes to 0, you have infinite diffusivity. This is not hydrodynamics, okay? If you want to make Berni happy, you have to do omega close to 2 in order to have viscosity near 0, which means that you have to operate lattice-Boltzmann in the over-relaxation regime. And pretty deeply so. In those days, the first simulation we did with Benzi and Guerra, we used 1.89. I remember that because I called it the Benzi constant, right? And 89 is pretty close to 2. And if you analyze the relaxation scheme, you immediately see that there is no reason why the method should work in the over-relaxation regime. You have no guarantee that the distribution function remains positive. So why did it work? This was a big smile of Lady Luck. And the reason was found out almost 10 years later when Ilya Karlin, another lucky instance, visited me from Novosibirsk, I think, no, Krasnoyarsk, okay. And Ilya was an expert in entropy, and as he visited, we immediately jumped on the fact that there should be an H theorem into the lattice-Boltzmann, and in fact, we were able to show that the lattice-Boltzmann we were using not only had the right conservation property, but it was also compliant with the H theorem, and that led to the first paper on entropy lattice-Boltzmann, which is 1998, so almost 10 years later. And nowadays, Ilya is probably, I think for turbulence, the best entropic method. Entropy lattice-Boltzmann is really, in my opinion, the best method, and you can see that these results are really top of the line. So there you really compete with computational fluid dynamics. So that is the equation in full splendor, and even though my wife is sitting here in the audience, I must say that I'm in love with this equation because each time she knows. She blames on me. I know Boltzmann for longer than I know her because I did my thesis in it on Boltzmann. She said, all your life long with Boltzmann. Well, I had a lot of fun with it. I did many things. So I have an excuse for that. This equation, I'm sorry, this is beautiful. It's pure beauty. And each time I look into this equation, I can hear her speaking and telling me, look, there is more you can do. And if there is one single credit I feel like taking in these long stories, that I always felt like there is more than fluid dynamics into this equation. And it is true, because just bear with me just a little second. I don't want to be technical, but there are several remarkable ingredients. First of all, streaming. C sub I is a lattice, you see the lattice discrete vector. So I'm a mover on the right, and I'm blank. I'm still an automaton in this way. When the tick comes, I do this, if I'm a right mover. If I'm a front mover, and I'm still blind, when the tick comes, I do that. Everything is synchronous. No thinking. This is the lattice of okay. I'm sorry. I tend to move a lot when I get particularly excited. Thank you. Okay, now look at the left-hand side. This is the free streaming. Now the programmers in the audience would immediately recognize that here we are still caching on the lattice gas. This operation has 0 round off. This is exact on the computer. It's just a memory shift. we do motion for, free of round-off. Now compare with any fluid dynamic representation. This is structural, it's not an option. When you have Navier-Stokes, you have U grad U. You move information across the material line, which is the velocity itself. And this is a mess. In a turbulent flow, the velocity field is very complicated. In a foam, it's even more complicated. In lattice-Boltzmann, life is always simple in that respect. Life is straight. You only move information always along straight lines. If there is one little secret you take home from this lecture, is this. Information always move along straight lines. It's an enormous advantage, and especially when you have a low viscosity, okay? That's the reason why we can go to low viscosity. There is a second crucial property, which is a bit less straight, but equally important, is that we are used to dissipation. Dissipation is a Laplace operator in any fluid dynamic representation, but dissipation is an emergent property. It doesn't exist at atomic level. At atomic level, you have collision and you have relaxation. In lattice-Boltzmann, space and time are always first order, no Laplace operator. And if you do complicated boundary like Berni was mentioning, taking Laplacians around a shape, complex shape like a car or an airplane, it's a pain in the neck. It's error prone, etc. It's very practical, but very important that in lattice-Boltzmann, the nonlinearity is local, okay? The equilibrium is a quadratic function of the velocity because fluid dynamics is quadratic, but it's local. And the non-locality, the shift in space and time, is linear because this is a linear operator. In any macroscopic representation, the two are tangled. This is a great advantage. This is kinetic theory in general, and particularly lattice-Boltzmann. And there is a last ingredient I will not have much time to comment, but this also is a game changer. The way you couple to the external world, and I would say even more so, the way you couple with the internal world, I will come to that if I have time, but this is the way you code for multi-phase physics, and I promise you can do that in 20 lines of code. You change completely the complexity. You move from plain Navier-Stokes to multi-phase flow just in 20 lines of code. So this is beautiful, and for some reason I always felt there was more. And just as a proof, this is not a mainstream. This, I think, is a paper where I had most fun in my life. I did it out of pure fun. You may or may not believe it, but it is true. You can do Schrödinger equation. You just write a lattice-Boltzmann. Actually, you can prove that the Dirac equation in one dimension is a lattice-Boltzmann. It's not an approximation, it's exact. And you can also show that the way Dirac goes to Schrödinger in the limit of beta going to zero, non-relativistic, is pretty much the way Boltzmann goes into Navier-Stokes. And cashing on this analogy, you can write actually a quantum lattice Boltzmann. And only recently, I discovered that quantum lattice Boltzmann is a random quantum walk, which apparently is a big thing. This paper, Haronovic, Davidovich-Zaguri, is the inventor of the quantum random walk, which they tell me is relevant to quantum computing. And actually, our paper, which was just matter of fun, was posted just 3 months later. This, I don't know, just as a curiosity. I have to say this is not a mainstream, presumably because people know how to deal with the Schrödinger equation better than, I think Schrödinger, don't get offended, is probably easier than Navier-Stokes to solve. So, but I mean, you may argue. Okay. So, is LB perfect? Of course not. Dark sides of LB moon, but why should I tell you, after all? I mean, well, I do, because we have to be honest. Many things. I don't want to be. Let me just mention the fact that we are still working. I promise you, you design car using this simple lattice. Some engineers will still laugh at you. I definitely remember a meeting in Amsterdam organized by Bernd Schmidt. I don't know, I saw Bernd around in 1980, I don't know what, 9. And I was talking to a lady, prominent lady doing all the recovery, and she at some point said, but do you work with the uniform grid? Yes. She was really disgusted. I remember that. And so, just to say that there are several limitations, I would say the most relevant one is one where Berni, is strange that he didn't mention that, actually. He wrote a paper very critical of lattice-Boltzmann when you have to do thermal physics, thermal and highly compressible, because never forget, lattice-Boltzmann is athermal. We don't have a continuous distribution, we have a series of beams. This is not thermodynamics, by no means. And this shows, if you really have a highly compressible flow with a lot of heat exchange, So just to say, no, lattice-Boltzmann is not perfect, fine, agreed. Let me move on now. And why is it good then? Oh, yeah, I owe this. So this is a long ride. When I look at this, frankly speaking, it's difficult not to be kind of moved. You know, I'm getting old. This is a major ride. I mean, this was the lattice gas. There were vortices. Feynman himself got excited. Leo Kadanoff got excited. Frisch got excited. But as soon as they couldn't go to this level, they quit, period. It was no longer fascinating to them. I understand that perfectly. They quit, period. For some strange reason, Francisco Higuera, who brought so much in it, we did these papers in 1989, and then he disappeared. I never asked him. By the way, he's not a very talkative guy, as you know. And I have to mention Stephen Orseg, which unfortunately passed away years ago, was a splendid friend and mentor. I salute Steve. And he was really instrumental in taking lattice-Boltzmann from a decent fluid dynamics tool into highly competitive. This is a calculation done by EXA Corporation, which was now has been absorbed by the Dassault Group for NASA, and that's leading edge. And with Steve was a strong advocate of lattice-Boltzmann for turbulence modeling, okay, which is not exactly what Berni has in mind, but is similar. And the principle of turbulence modeling are published in a paper we did in 2003 in Science. So that ends the fluid dynamic part. And now we get closer to CECAM, how to go actually closer to complex fluids and soft matter. This is a foam, which we simulated a few years ago in Rome. And I go back to the story. Leo Kadanoff, as I said, he was very, very interested in the cellular automata. And the point was, the mantra was a simple model for complex flows. The beauty of simplicity of the automata, which gives complexity at the emergent level. Now, is lattice-Boltzmann a simple model for complex fluids? Yes and no. It's certainly much simpler than any non-ideal computational fluid dynamics based on grid discretization, but certainly is much more complicated than the easy model or a plain cellular automata. I really like the way Tony Ladd put it. He once told me, or wrote, I don't remember, lattice-Boltzmann is very cost-effective. If you look for the 7th digit, it's probably not your best method, okay? In almost, not all, application, you can find the specific method which is more accurate, but the learning curve is much, much steeper. Lattice-Boltzmann is sweet because it provides access to complexity at a cheap cost. Do not expect the 5th digit, all right? And the good thing is that it can never be too wrong. I really like the way Tony put it this way. So I see lattice-Boltzmann as a tool of exploration, and Dan has a fantastic paper on the limitation of what was the title of your paper? What you learn by computational, by simulation which fail, which is, I mean, it's a must read. This paper is fantastic. So eventually lattice-Boltzmann would fail, but hardly fails really flat on his face. So it's extremely useful in this respect, to gain information in complex problems without making your life too miserable. Here I have to cite something which goes in the line of simple model for complex fluid. This is a beautiful paper. It's worth actually a lecture on its own. Xiaowen Shan and Dong Chen, they find a way of putting potential energy to the game in a very clever way, just using first neighbor potential, only attraction. And now, of course, you cry against me, I mean, you scream, because we all know that in order to have phase transition, we need repulsion attraction. No, that's not true. There are tricks which I will not be able to explain, but if you use the proper trick, the proper pseudopotential, you can trigger phase transition with attraction only, provided the attraction strength depends on the density. This has also generated the mainstream, multi-phase microfluidics, and Julia, I don't know whether she's still here, she also has a very significant contribution to this area. Another major mainstream nowadays, and again, I have to credit Tony, and there are many, actually, faces you recognize here, Ignacio, Dan, of course, Burkhardt. Tony, again, I want to make this long story short, he found a way of injecting fluctuations into the lattice boson to do nanofluidics, to move colloids. I think that's what Berni was referring to, and we're talking 1992, 93, so a few years later. And here again, I'm old enough to have an episode, personal anecdote, which attests to my stupidity, so to say. I have to quote Tony Mail. I was at IBM, and I get an email by Tony saying, Saro, what do you think of putting noise into lattice boson? And then I was still busy with turbo, and I said, look, Tony, why do you are asking this? I mean, we did so much work to get rid of noise, now you want to put it back. And then, why do you want to do that? And he did it, and good for him that he didn't listen to me, because this has really generated another mainstream. How much time do we have?
Minutes.
Okay, so I'm way beyond. Okay, so I will make a long story short. I think we can still go beyond, and again, I think that's an area which is very relevant to CECAM, how to explore mesoland, situations which are too small for continuum, too large for atomistic, and I discovered actually lately, in the last 10 years, we found many situations in soft matter where this is true, where in fact you don't need to jump directly from Navier-Stokes to molecular dynamics, there is something in between, and with proper adjustment, lattice boson can do an excellent work in this mesoland area. And so let me move fast. You have to do something more complicated. I mean, I'm not sure you can call this a simple method this is a significantly more elaborated lattice. Just trust me if I say that you can go beyond local equilibrium here, okay? Which was absolutely forbidden. There was a comment in PRL say, you are reckless, this is an uncontrolled approximation, we don't have asymptotic theory for that, you are just doing, it was very aggressive. And since they were so aggressive, my reply was kind of polemic. If you have full analytical backup, where is the fun? And actually, where is the use of simulation? It's very fun, actually, to go in a territory where your only protection is your own where you are on your own and you don't have analytical backup. There are many, many situations like this. And now we are using them for my ERC. I just want to mention one thing, like this. I just want to mention that there is another bonus of lattice boson that if you work hard enough, it doesn't come for free. Parallelization always pays off. And this is a roadmap of the code which we developed. It started all in Harvard with Tim Caxiras, Massimo and Simone. Just let me mention the end result. In 2013, this is the Gordon Bell, is a major worldwide supercomputing contest. We were in the final 3 times, and this calculation is a protein aggregation within a cell with some 50,000 proteins, each containing 4,000 particles, and this reached 26 petaflop, which is still close to the world record. If I could, which I can't, extrapolate the Muffy roadmap, we would have been on an EXA line 2 years ago. Of course, this is a crazy thing to do, but we are ready. As soon as the Titan became operational, I think we can imagine, and this would be interesting to discuss with you, that would be a talk on its own, how to simulate an EXA molecule, namely an organelle. I think Golgi would be probably feasible at that level. It would be fantastic to have a try on that, if we get the machine. Beyond Newton, now I'm getting wild. 3 years ago, APL asked me for a perspective. I had a lot of fun in writing the perspective, and I said, I don't want to talk about the present, I talk about the past, as I did today, and I talk about the future. Can we go beyond Newton? And actually, I always felt like relativity is more suitable to kinetic theory than non-relativity. I was partially right, because the streaming is easier, but the equilibrium is much more complicated. And by good fortune, I was visiting ATH those days, and Miller Mendoza, in his PhD, actually worked out all the details. And I just gave me the result. It turns out that we could actually, there are very strange fluids around in the femtohydro, in the QCD, in the CERN area done, where actually, which have minimum viscosity to entropy ratio, less than a superconductor, in fact. And graphene, electrons in graphene are one of them, so we did this relativistic simulation. We predict there could be sort of pre-turbulence in graphene. We talked to the professional graphene, including André Geim, but unfortunately the frequency is still too high for the experiment, so the prediction is standing. We'll see whether it comes true. And something I was discussing with Ignacio, I think there is an opportunity. I think maybe we should organize something with CECAM and CERN done. These are fluids where, in fact, this is the smallest droplet in the world. And actually, you are totally right. They made such a big fuss of this. Say this is the smallest droplet in the world. It's just 5 to 6 femtometers. There are just a few quarks around with all the gluons dancing around. And believe it or not, this obeys hydrodynamics, relativistic one. So I think the relativistic lattice-Boltzmann, and this is the latest work done in Ferrara, could actually be used, and I'm tempted to go very seriously in this direction to study actually femtohydrodynamics, which would bring actually a sort of interpolation between LHC, where these games are played for real, and CECAM. Why not? We'll discuss that later, right? Big bang, small bang, blah, blah, blah. Thanks time. I have 3 minutes for thank you. Okay. It's a long session, thanks time. First, thanks to the two great men. Ludwig, for inventing it all, like in advertisement, no Boltzmann, no lattice Boltzmann, right? It's literally true. Berni knows how to advertise himself. He still does, as you see. But he deserves it fully to CECAM, no questions. Alessandro, Ignacio, Sara. I beg your pardon, Sara, for not putting your name, but Sara is doing great work, and I know her since long. Of course, how would I forget my nominator? Some of them I do know, by the way, after fact. And the committee, I'm really very, very grateful for. It's an immense honor. I mean, I hope I'm hiding it, but I really feel emotional because I love Berni and I have so many good friends here, and I always regarded, and I mean it, you know that I mean it, I always regarded this community, I have the lattice Boltzmann community, which is strict on the lattice Boltzmann, but I always regarded this community as my community at large. I really invariably enjoy very much the meetings organized by CECAM. I should have been in more than I could possibly do, but you know, I'm not able to teleport myself. So, first, thanks number one. Oh, by the way, this I owe to Chris Delago. He has a marvelous paper asking, what would have Boltzmann done? You know Chris, right? I read it. Had he known about computers, and Chris predicted he would have definitely invented molecular dynamics, I agree, and I bet he would have invented lattice Boltzmann. Actually, I'm sure, I cannot ask him, but I'm sure if you read in the Boltzmann in unreadable book, Vorlesung über gas theory, he says, right explicitly, that a discrete velocity representation of his horrible collision operator is way more physical. So Boltzmann knew about lattice Boltzmann, okay? And so I owe him thanks. Other thanks I owe, of course, to the CECAM community. I don't know how much time, because I have a comment for each of them. Maybe I should skip it. Just let me comment on Giovanni. You always have time to comment, and of course I have to badmouth him. Giovanni, he first, I think, introduced me to CECAM, but which is a great, I'm indebted for a life. But I'm even more indebted because, actually, you know Giovanni, when he gives a talk, he gives you basically 1 picosecond between one question and the next, right? He gives the speaker an absolutely impossible time. He never did that with me, so I'm very, very grateful to Giovanni. Dan, what should I say? Dan, he knows. Each time I have some crazy idea, I double check with Dan because I trust that what comes back will be definitely correct. Dan not only responds immediately, it always responds in a way where I learn, and it always comes with a lot of fun. And as we all know Dan, you know, if by someday you feel you're smart, you talk to Dan and then you think twice, right? But not that he would impose anything on you, just come by very nature. So I really have an affection for all these people. Michel, organized this fantastic workshop, and we had a lot of exchange. He taught me a lot of molecular dynamics in the early day. Christoph already said, and Christoph gave me a major privilege that I could lodge at the Boltzmann Hotel in Vienna. Fantastic experience. Then Jean-Pierre always treated me like a gentleman he is, and I am not, manifestly. Kurt impressed me incredibly. I had an exchange with Kurt half of an hour in Mainz, and immediately taught me something. He taught me that if you want to do lattice Boltzmann nanofluids, you have to go below angstrom, which I thought was a crime, and immediately got the point. And Michele was gentle enough. I went to him with the idea of coupling lattice Boltzmann and Carparinello, which is totally insane. And he just sneered at me, but never told me that I am insane. So I'm very grateful to him. Finally, all my friends in lattice Boltzmann, many institutions, starting from IBM, I would say. That's where it all started with me as a programming exercise. Never forget the family, right? We have a lot of passion, and we put the pressure on the family, so I have to thank the two Cs, Claudia and Caterina, which are sitting over there, for bearing with me. We know the story, right? So they say, don't forget to do that. You regularly forget, and they forgive you, which is not obvious. And I like to finish in a dramatic way, citing perhaps the most famous Italian, which is San Francesco d'Assisi. Giovanni, I know you are not a believer, but San Francesco is very respectable. we are sitting on different fronts, but we love each other nevertheless. And he has a beautiful statement, which I know for a long time, and I really think, with all due respect, I can apply it. He says, in Italian, I think you can read, start by doing what is necessary, then do what is possible, and just all of a sudden you will be surprised that you are doing the impossible. Now, with all due respect, of course, I started to do what was necessary. It was necessary for me to program the automaton, right? I had no choice. This was my job. And then we find that it was possible to go beyond that, doing the first lattice Boltzmanns. And I don't want to be bold, but frankly speaking, some of the things we do today with lattice Boltzmann were actually declared, stated as impossible in PRL, not just in a minor journal. So I'm very proud that we do things which were deemed to be impossible. And last but not least, if they had told me, I go back to Alghero 30 years ago almost, that many years down the line I would sit here in this audience for this immensely appreciated, and really I cannot believe it, award, I would definitely said impossible, mission impossible, and it happened. So thank you all for making this happen. Thank you.
Well, thanks very, very much, Sauro, for this fantastic presentation. We really, really enjoyed it. So this quotation by Francesco d'Assisi also give us the excuse to move to the most formal part of this ceremony, which is the award of the prize itself. The prize will be awarded by Hardy Gross, who is here. He's actually he is the winner of the last edition before this one 3 years ago. So we decided that it was like passing from one winner to the next one was the best manner. So please, Hardy.
Yes. So as a representative of the prize committee, it is my job to read to you the formal prize citation, and this is what I will do now. So the Berni J. Alder CECAM Prize of 2019 is awarded to Sauro Succi, professor at La Sapienza in Rome at the Center for Life Nanosciences. Sauro Succi is a pioneer of the lattice Boltzmann method. In 1989, he was instrumental for the first lattice Boltzmann nonlinear flow simulation, and shortly after, for contributing to the highly influential top-down interpretation. Following these groundbreaking contributions, he authored a multitude of early fluid dynamic applications and spearheaded developments which made the approach suitable for modeling flows far from equilibrium, up to inserting the Lattice-Boltzmann method into a multi-scale approach. Over the decades, he has obtained outstanding results. He has continued to lay out and to consolidate the foundations of the Lattice-Boltzmann method, to open it up to new applications and to extend the approach beyond hydrodynamics into new territories of micro and nanofluidics, porous media, soft matter, and electronic transport. Overall, Sauro Suchi has transformed the Lattice-Boltzmann method into an overarching framework for kinetic physical phenomena. In addition, he has been pivotal in building and constantly inspiring a community now counting tens of thousands of researchers in academia and industry, all across chemistry and physics, and reaching into more distant fields such as engineering and biology. Sauro, my warmest congratulations.
So congratulations again, Sauro. So that's all for this first part of the afternoon. So we'll go now for the coffee. Remember that we first have to go to the group photo upstairs and to the terrace. Let's do that fast so that we have some time for the coffee and reconvene at 4:30.